Quick intro before we dive into the podcast. I'm really excited to share this conversation that I had with a structural engineer, Trevor Acorn, who I really admire. But I also want to let you know that this is a very technical conversation. So if you are not in construction or engineering or architecture or, the act of putting buildings together, this might be a pretty boring episode and you might want to skip it. But for those who are nerds about this kind of stuff like me, you might find it really interesting. Hope you guys enjoy. All right, well, welcome to the Building Culture Podcast. I'm Austin Tennell, and I'm super excited today because I've got on Trevor Acorn, who is a structural engineer, and from my understanding, a principal at Walter P. Moore, which is, like a global engineering firm. And I first ran across you, I think, on Twitter when I was in Spain, like 4 or 5 months ago or
Right.
something. You commented, and I looked up, and you just had a very fascinating take on things. I've never talked to a structural engineer who is talking like you. So before we get into that, if you could just do a little intro, talk about, your background, what you're doing now, stuff like that.
Yeah, no problem. Well, yeah, like you said, I'm a structural engineer. I work for Walter P. Moore. Walter P. Moore, it's a global engineering firm, and we primarily do structural engineering, um, and we do a lot of pretty large and well-known projects all over the United States and even the rest of the world. But we also do enclosure engineering. We do diagnostics on old buildings. And so my particular role is structural engineering. I'm a senior project manager here at Walter P. Moore. But I've got friends just down the hall that specialize in restoration of old masonry or glass facade restoration. We have guys that specialize in civil engineering. I mean, we have a lot of groups all in one firm. And honestly, it's pretty great to have so many experts under one roof that I can tap into and ask questions. But yeah, so that's me. I've been practicing for 18 years, mostly in buildings. There's a lot of structural engineers that do bridges and other specialty, but I'm a I'm an engineer of record for many projects. Primarily work in the big materials, steel, concrete, masonry, um, and yeah, I do projects all over the U.S. Been in Kansas City for about 10 years here,
Where are
and
you
it's great.
from?
I love what I do.
Where were you before that?
Well, so my folks lived outside of Rolla, so I grew up kind of in rural Missouri. Went to school in Rolla. There's an engineering school there that's fairly well known. Spent a couple years in St. Louis, but then came over to Kansas City.
Got
It's
it.
a lot of engineering here in Kansas City. It's a good place to be if you're an engineer.
Cool. Well, we'll get into like defining some of the things we're talking about later, like what is structural masonry and all that. But I'm
Sure.
actually just curious, like how, because most structural engineers that I interact with, right, and they could walk all over me in terms of engineering, right? Like I don't know how to engineer things and calculate numbers and all that. But I've been consistently surprised at people's non-understanding or at least misunderstanding or whatever you want to call it about masonry, structural masonry, and just like knowing anything at all. Like most people don't know anything about structural masonry. How did you, you know, how did you get familiar with that, with structural masonry? Like, have you worked on it? Is it because there was people doing restorations? Do you have an interest in it? Where does that come from?
Yeah, I came at it on from the latter two. So um, 12 years ago, I bought an old house and it has structural masonry walls, right? And I had to have one wall rebuilt completely because the mortar had been repointed with a type S mortar.
Uh-huh.
Over time that had cracked, water had infiltrated the wall, it had washed out the lime mortar that was behind the face mortar. All that mortar then kind of ran back behind the wall and filled up the cavity. It's kind of an interesting thing here about Kansas City. We have all these shirtwaist homes, and they were some of the earliest cavity wall construction. So it was like 6-inch stone, but they do have like a 2-inch air gap back there. But it was all lime mortar. They use these large nails to tie the stonework to the wall. It's
Huh.
really unique. It wasn't done for very long, but
What
but
and what
anyway,
kind of
like that
wall was it? You
whole
said because it's 6 inches of stone, but what
right,
is the
6 to
quote
8
unquote
inches.
wall?
Yeah, it's almost a precursor to modern cavity wall construction. It was done in the 20s, actually earlier than that. My house is 1905, but they would do a rubble stone foundation, right? And then they would set a wood floor on top of it. And then that last kind of width of stone, they would take up a whole story. And
Mm.
so that would be tied back to the stud wall cavity.
Okay,
So
and you're saying
structural
when it is a
masonry
stud wall, it's
below,
like 2x4,
right?
old growth 2x4. Is it siding like 1x12 slanted or something like that for your like
Yeah,
sheathing?
right.
Okay,
Yeah, it was one by sheathing. So it's structural masonry, the kind you're familiar with, the kind you're working with, below grade, right? It's a
got it,
rubble stone foundation. But
got
then
it,
once you get above that, it turns into a cavity wall system, and it was a very early version of a cavity wall system.
got it.
But yeah,
Okay,
working on this old house and then understanding why the wall was failing, it led me down this rabbit hole of understanding the different types of mortar, different types of construction, our particular type of construction here in Kansas City, and also just you know historic masonry restoration generally. We have experts, like I said, at Walter P. Moore that do that work, and so I've had a lot of conversations with them as well. So. You know, over the past 12 years, I've just gotten really familiar with it, primarily through this side, the side of restoration, not new
hmm,
construction, because again, you're like one of the only people doing that. But on
right.
the restoration side, it's common. It's
No, I
common
found
to have
that
to understand
restoration
it.
people are actually the most generally helpful people to talk to
Right.
because they know things from experience that they have seen. It's not because they heard something or it's an old wives' tale or blah blah blah. It's no. If you put Type S mortar, tuck point Type S mortar on top of lime, it will destroy your building. Like they can
Yeah.
say things
Right.
with confidence from real experience of things they've seen that have lasted 100 something years. Although I will say there's a little. It's interesting. Actually, I want to take your temperature on this. So there have
Sure.
been a few restoration people that have pushed back on my claims that well I say this term a lot, like one that all the oldest buildings in the world are some form of structural masonry. And I say all, maybe I should say the vast majority of, right? Because whether it's the
Mhm.
pyramids or the Pantheon or entire cities all over Europe or South America or even in the Middle East or something, it's structural masonry. And some people have kind of suggested that I was getting confused and like saying I was making like a logical mistake of calling it survivorship bias. But for me, I'm actually saying like I think they're using that backwards because the restoration people that are saying this, they'll say like, no, every masonry building we work on, you've got to retuck point the whole thing. It's hundreds of thousands of dollars, blah, blah, blah. And I'm like, yeah, because it's still there 150 years later when it hasn't been maintained versus stick frame left unmaintained would not be there in that time. Because that's how I describe it as masonry. It's not like one is inherently like better. Everything's got pros and cons, but masonry has fewer vulnerabilities. Take out seismic and then it's not termite, mold, fire, rot. It's just less things, vulnerabilities than mason or than wood framed construction. Would you kind of
Yeah.
agree with that? Would you argue? Would you add on to what I'm saying here?
Sure. I mean, boy, any building that's poorly built and not detailed well is just not going to last, right? And even a structural masonry wall, if your roof is improperly designed and it doesn't shed water properly, if that masonry is constantly exposed to moisture and freeze thaw, I think it's going to have a limited life. It's going to last a lot longer than wood. I agree with you there. But every building needs to have good detailing to
Yeah.
last, and I think that's an important point. One thing I've seen a lot, just looking at all these old so I live in a historic neighborhood of Kansas City. I'm surrounded by masonry buildings, and a lot of that masonry done with lime mortar over 100 years ago is due for repointing. It only needs to be repointed once every 30, 40, 50 years, right?
Right.
It lasts a really, really long time. But it's important to do that right. And when it's done incorrectly, then those buildings fail prematurely. And I think there's also something to be said too about modern mortars. I'm not a huge fan of high cement mortars, but
Mm-hmm.
a well-designed, well-engineered masonry building today, like the ones you guys are doing, even with exposure to water, are going to last even longer than some of the historic ones that are being built.
Yeah.
So I think doing it right makes a big difference.
No, I like what you say there that it needs to be detailed right because I've seen old brick buildings that are in terrible shape, as you're
Right.
saying. And the thing that I would say is kind of like you're saying is that it can just go a much longer period without being maintained. and
Hmm.
still be able to be brought back to life with serious maintenance and stuff and fixing it up. But what I'm thinking about, like part of our argument is if you're trying to build for centuries, obviously you want to detail it all well,
Yeah,
regardless of what you're building. But you also don't want to assume that there's going to be like perfect maintenance all the time over a 400 or 500 year lifespan.
exactly
You know,
right. Yeah,
economies, and when you talking about that kind of time span, you're talking about like six cities, you know, becoming very, you know, wealthy and then kind of falling into poverty for 100 years and then back, you know, like it's a long and so I think that's part of the strength of masonry is its ability to withstand years of neglect when built correctly. And it's not indefinite,
right.
you know, it will disintegrate at some point, you know, the mortar and all that.
Yeah, I think I certainly talk a lot with people about designing a building well from a structural perspective, from a durability perspective. But I think something that you're onto, and I think the rest of the AEC industry, I wish was onto more, is designing buildings that we love, right? Because if
Yeah.
we build a beautiful building, it's going to want to be maintained by the people that own and live in that building, right? People don't want to
Yeah.
see beautiful buildings. Um, go into disrepair. And I think that that's also an important factor. I think the design is really important aesthetically. The details are important. I mean, all the stuff is really important, right? My goal in life is for all of us to build better buildings, buildings that
Yep.
last, um, buildings that we can give to our kids.
No, that's I love it. Yeah. And I actually want to come back to talking more about that because that's really unique. Well, I think it's a neat perspective and it's really unique in like engineers. Like I've just never talked and like on your bio, you're like talking about Christopher Alexander and stuff. Like how did you get how
Yeah,
did you, you
sure.
know,
Yeah.
Donald Shoup and stuff? Like how are you
Yeah,
you
I could talk about that a bit. I mean, so my my engineering my, my education was in architectural engineering, and there's a lot in that program, of course. But I did 2 semesters of a history of architecture class. I had a really great professor, Jeff, there, and during that class, I got introduced to Christopher Alexander and just to architectural theory in general, and I really fell in love with it. It just really hit on a lot of levels for me, and so I went down a pretty deep rabbit hole in the whole new urbanism and these the Christopher Alexander kind of way of thinking and looking at the world. Um, that led me into a lot of other things, including thinking about like urban economics, right? And Henry George and Don Shoup and these other things that impact our built environment, right? It's not
yeah,
to me, it's not just our buildings. It's the whole soup, right? It's how everything comes together that
right.
really
And
matters.
gosh, we need like that is if there was one thing I could change about the industry. I mean, I'm kind of saying this offhand, so maybe if I thought
Right.
hard enough, I'd think of something else. But like if there was one thing that I could change about the industry just with the snap of my fingers, it would be to just have everyone be more well-rounded and understand what other people are doing. So engineers
Yeah,
understand architecture and architecture and engineers and GCs and trades and
100%.
utility engineers and municipalities like they actually have an understanding and appreciation. It doesn't mean they're experts, right? But like yeah,
Yeah, totally. One of the best things I did was working for my dad in construction during
oh,
college. He was a builder. He had a concrete company, and I would help him pour concrete, and I did flat work and elevated work, and
that's
um,
cool.
yeah, it really made me appreciate what gets done in the field, and I keep thinking back on that. Another thing too, after I graduated, I went to work in St. Louis for this development called the New Town at St. Charles, which is a new urban development, one of the larger ones in the United States. It's designed by Dwayne Plater Zybeck, so Andre Swanee was a part of that. And I got to work with Tim Bussey, the town architect, and it was really cool. I mean, I lived there, I was part of that whole group. But also, like as we're designing and building all these buildings, I'm kind of the in-house structural engineer for them. The guys that are actually building all the buildings on site are coming, just walking in the door because our office was right there on site. They'd walk in the door and they'd share their comments and they look at me and they'd be like, Trevor, I need you to design this differently for this reason, right? Like I wanted to put this together like this, but the way you designed it doesn't allow me to do that. And so I got constant feedback from these guys in the field that allowed me to be a better designer.
Wow, that
And
is so cool.
Yeah, and it's something that I've always, when I design a new building and I go out on site visits, I'm always asking the contractor, hey, what could I have done different? Like what was a pain point for you? What slowed you down? Those kind of questions, right? Because it really matters that the people building the building aren't frustrated as they build it, right? And that they can deliver at a really high level. I
Yeah.
think that's important.
Man, yeah, very cool. I could keep talking about this for 20 minutes, but I'm going to kind of move on because I want to get through get into some of
Sure.
the technical stuff. And part of it, I actually want to talk about the industry more from my own understanding. And like, if you were to describe to a sixth grader, right? So as if I'm an idiot, well, sixth graders aren't idiots, but you know what I mean. Describe to me like I don't know what I'm talking about. What does it mean to engineer something? Like, what are you doing? Does that question make sense?
Yeah, sure.
Okay.
Yeah. Well, I think a lot of people know what it means to design something, right?
Yeah.
And maybe we should start there because engineering is really the next step. It comes uh, behind the designer and it helps the designer accomplish his design, right? So I work primarily for architects. So I'm a consultant to an architect. They come up with a beautiful design for a building, and somehow they need to get that thing built in the real world, right? And so they come to me and I design the structure. So I'm designing the columns, the beams, maybe the stud framing, the foundations, all the things that are required to make that building actually stand up and work, right, in the real world, for wind, for seismic, for gravity loads. So that's the particular kind of engineering that I'm doing. I'm supporting an architect who's doing design work, and I'm doing the engineering behind it.
And then, and to go a layer deeper,
Yep.
because then when you say I'm designing the beams, I'm designing the structure, once again, like, what do you mean by I'm designing? Because, like, I know what it means. Like, you're running
Yeah.
calculations of load and all that, and PSI and compression and shear and all that. But there's, and this is where I start to really not know what I'm talking about. There's even different ways that you can choose as a structural engineer to analyze something, right? There's not just one way to engineer a beam. Aren't there, multiple ways to analyze something? Am I right about that? And like, they've got names, or is it just like
Sure.
one approach to everything?
Yeah, it kind of is material specific. And we also, we have building codes, like we have the International Building Code, International Residential Code, that provides guidance and rules and limits on to, where you go with your design. So there's a lot of guidance out there, and there are different ways to do it for sure. There's different approaches to doing the math, to doing the analysis, and to picking the beams. Um, but they're all pretty similar, right? So in my world, a more technical term, like we have ASD, which is an allowable stress design method.
That's okay. Yeah.
Yeah, and so we'll use that. That's very common in masonry, for example. It's really common in wood construction. But in concrete and steel, especially concrete, we have LRFD, which is, let's see, load resistance factor design. So it's more of a statistical approach um, that takes the loading, but then applies it in a little different way than the allowable stress design. Two different approaches. They actually, I mean, honestly, they result in very similar kind of
Got it.
answers. But that's just, I would say that's just on the strength side of things. As a structural engineer, I'm also thinking about the stiffness of things. That's like deflection, right? And how they perform. So like deflection, but also vibration is a concern. Um, I'm also concerned about, seismic forces, wind forces, um, and of course how all these parts and pieces of a building come together. So um, there are nuances to all that, and different structural engineers have different levels of experience in those areas. For example, not every structural engineer spends a lot of time doing vibration design, and there's a lot of
Mm.
nuance to vibration design or to high seismic design, and it takes experience to do that well. So like, one thing that I'm doing with my architects is I'm trying to bring the best practices of design, of structural design and engineering to the table. And if it's not, that may not just be through me, right? But through my team or through my coworkers in California or New York or wherever they are, we bring the top designers to the table on some of these buildings that we work on.
Got it.
Hope that
Okay.
helps. Yeah.
Yeah, no, it is, and that's what I was looking for. It's like the AST allow. What is it? Allowable stress
Allowable
test.
stress design. Yeah.
Allowable stress design. Okay, and then load resistant something.
Factor. Yeah.
Yeah,
Load resistance factor design.
got it. Okay, and in terms of, and you might not know all this if you were to ask me the history of my profession, I couldn't tell you certain things, but what when I say, or when we say modern engineering, what does it actually mean to you? Like, is there a date where it's like, now we are crossed into modern engineering? Here's pre-modern, here's post-modern engineering, or just modern
Yeah.
engineering, I should
I'm
say.
not an expert in the history there, but I do know that a lot of these methods of analysis and engineering started to come about in the early 1900s, the 20th century, late uh, late 1900s, early 1900s, and we just started using, using physics, science to the built environment. So before that, a lot of things were built on an empirical method, right, based on experience. A lot of the masonry buildings all around the world, they were built on essentially rules of thumb, right,
Right.
of best practices kind of learned over time. And modern engineering just applies the foundations of physics, structural analysis, um, uh, statistics to buildings, so that we can kind of tune that and think about it a little more logically, right? We can
Got it. Yeah.
calculate the forces that go through a beam, and we can figure out exactly how many bolts it's going to take to hold that beam
Yeah.
up, right?
Kind of a random offhand question.
Sure.
Do modern engineers believe in the idea of thrust, that an arch or something lets off thrust? Because someone told me they don't.
It's an interesting question. I don't know if I feel like I should ask about whoever told you that. But yeah, of course,
Okay.
it's yeah, thrust. We don't run into it as much, right? Because we're not building arches
Right.
anymore so much. It's much more rare. But anytime you really do have an arch, then you have thrust. The most common place that we run into thrust is actually in an attic roof of a house, right? If you think about any attic roof, you got two rafters that they're coming together, and at the base of those rafters is thrust, right?
Yep.
Without something to resist that thrust at the bottom of the rafters, those rafters will spread.
Yep.
And so normally we resist that with the ceiling joist, right? Or if you have a prefabricated truss, I mean, that's what a truss
Right.
is it's got a bottom cord that resists that thrust from the rafters. So
Got
yeah,
it.
I mean, thrust
And
is
can you
very,
calculate
very real.
specifically, like, what is the thrust coming off of an arch? Say, hey, it's 20-foot wide arch, you got X amount of weight above it. Can you, and how do you do that in modern engineering? Because I've not met many people. You're and we'll get into graphic static. There's so
Sure.
many things I want to ask you.
Yeah.
Gosh. Okay. So I'm trying to not throw too much at you at once. Can
Um,
you calculate without graphic statics? Let's not get into graphic statics yet, but
sure.
just in kind of like modern engineering, do most structural engineers, could they look at an arch and be like, yeah, you need about 5 feet of buttress on this side of the arch to make sure the
No, I don't
forces.
think anybody could do that, honestly, anymore. It's
Okay.
so uncommon. Yeah,
So
like I
they know
said,
it
thrust
exists.
is a
They just
very
don't
real
know how to.
thing. Yeah, but that is, oh my goodness. Okay, we have specialty engineers that do very large structures, like tensile fabric structures and large uh, compression arch kind of structures, where they have specialty software that is used to calculate that, and define. A big part of these kind of structures is not just calculating it, but then finding the right form. We call it form finding, right? Because you have to you have to draw out your arch in the correct shape for it to be in pure compression. And if you do that incorrectly, then you can get bending moments inside your arch that cause it to fail. So it's really important to get the shape of an arch correct. Um, so yeah, we call that form finding. We use graphic statics, Rhino, Grasshopper, a lot of tools to do that.
Y'all use
Um,
graphic statics because, like, most. So is that you that knows graphic statics, or like, hey, most of the people you work with know it too?
Very few people I work with know it. Yeah,
Okay,
it's
I was gonna
it's
say, because I haven't
incredibly
talked to
uncommon.
anyone. You
Yeah,
were the first person. They were like, "Oh yeah, graphic statics." I was like, "Wow, I gotta talk to
yeah,
you."
yeah.
And
It's
I see the book behind you. I don't know if you can see mine.
oh
I've actually got it sitting right there. Uh, because when I was in Spain and I was like, I could tell everything so much of what they were talking about was over my head because I'm not an engineer, you know? And I was like,
Mhm.
hold on, what is the baby version of this so I can like teach myself some stuff? And they're like, oh, that Foreman Forces, that'll teach you everything. I like got the book and
Oh,
it's
that's the
just
book. Yeah, that's an
huge
incredible
and
book. Yeah,
complex. And I was like,
right.
whoa, okay, I'm not going to figure this out overnight. But um,
Definitely one of my favorite books. Yeah, no, okay, graphic statics would be used to find the shape of a truss well, it can be used for trusses, but for an arch, it would be used to find the shape of an arch. Or if you have an arch shape and you have some uniform applied loads to it, you could use it to calculate if that arch is acceptable or not.
or to calculate
Um,
how much buttressing you need,
right,
based
yeah,
on,
to
yeah.
calculate the buttress force or the thrust force for the buttress.
Yeah.
That can fall out of a graphic statics approach. Unfortunately, though, like when you get into different load combinations and wind pressures that maybe hit the arch in different ways, or if you have like a point load on part of the arch, it gets really complicated really quickly. And so that's where we use computer methods to define those forces and to check an arch under all the different load combinations and conditions that might apply in the real world.
Got it. Is
Yeah.
is
Yep.
struck is graphic statics? Is that like is it on the lines of say a type of analysis that modern engineering can do, like ASD, or LRFD, or is it kind of completely separate? Is it like official? You know what I mean? Like, or is it just, hey, this is a good way to think about things, or is it, hey, if you can prove it in graphic statics, you can pass code and do it?
Okay, yeah. I don't know of anyone using graphic statics as part of a calculation package that they then send to, the building official for permit. Um, it gets at the right answer, but again, you have to prove to a building official that whatever structure you're designing is going to work for all the different conditions. And when we talk about building a commercial building with all the different loads, we might have 1,000 different load combinations that get applied to any given beam or element in the structure. And it would be incredibly difficult to use graphic statics to do that. We would use graphic statics up front to find the shape, right? And to do the big
Interesting.
picture analysis. And then we would use a more robust computer software to fine tune that and to do the final calculations that would be submitted to the building official. In the end, it's not really ASD or LRFD. What it is a way to for any given load, define what the resultant forces are. It's a
Hmm.
trick, right?
Got it.
Um,
Is it accurate? And this is kind of like when I was hearing it from non I was hearing it from engineers, and I'm a non-engineer. And the way I've kind of been describing it since I kind of heard about it is graphic statics is a way to um, design a very efficient uh, design something very efficiently by considering the shape and the geometry and the flow of forces through a building or material, and kind of like tailoring it to that. So you're kind of getting rid of excess waste and excess materials and things like that, or it allows you to do stuff like that.
yeah,
Is
yeah, that's
that kind
absolutely right.
of, that is right? Like, I'm not
Yeah,
wrong when I
no,
say that?
that's absolutely right. So I
Huh.
mentioned earlier, we use it for form finding,
That's what I
right?
thought it was cool, because when you said it, I was like,
Yeah,
okay, maybe I'm not wrong when I say that.
yeah, it's really a tool for that upfront, finding the shape that's going to give us that expressive structure that we want, and that we're pretty confident that later when we do a more robust analysis is going to still work, right?
Is that the Eiffel Tower? You might not know this, but I think the Eiffel Tower and stuff was based on graphic statics. And do you
Yeah, I
know?
think it was actually.
Okay,
Yeah, I don't know much of the history there, but
man, there's this. Gosh, I
a lot
got
of
to.
older buildings were bridges, especially, were
I was about to
very
say
commonly
bridges.
done.
There was a
Yeah, that way.
new bridge. Gosh, somewhere in Europe. I mean, this. I mean, I wish I remembered the name of it. It really bothers me that I forgot it because I want to look it up. But it's just this, just thin bridge. It just has this little taper at the end across this huge gorge, and it's built in the past 10 years, and they
Hmm.
did it off graphic statics, and it's just, or at least this is what I was told.
Sure. Yeah,
And it's
it's
incredible.
awesome.
And of course, then you've got all the Guastavino stuff from 100 years ago that I'm getting really intrigued with, of learning how to do that. And this gets into the shape of the arch and things like that, because
Right.
I actually want to follow up with that, because assuming you've got enough buttressing, okay,
Okay.
assuming you've got a solid foundation with minimal movement and enough buttressing, so your thrust, isn't, going outside the wall or something like that.
Yeah, you've resolved your thrust into
You've
the
resolved that. In my
right.
mind, you could basically build an arch in any shape and it's not going to fail.
Well, as your arch, okay, so you have the spring line,
Yep.
you have the crown, the rise of the arch, and then you kind of have the top and bottom lines, right, which are the intrados and extrados, I think is what they
Mm-hmm.
call those.
Yep.
So we try to keep the flow of forces in the center third
Okay.
of
That's
the
what you're talking
intrados
about.
and extrados. Yeah. So as you adjust the shape of the arch, um, you have to do that in a way where that flow of forces stays within the center third of the arch.
Got it. Okay.
So that's why a flat arch, I mean, when you go completely flat, those
Right, a jack
forces no
arch or
longer
something.
resolve.
Or
Right.
so
Yeah.
what's interesting about that is, and I don't know this. I'm asking too. Like I'm both telling you what I think and asking you if this is correct. But that matters a lot when you're building, say, in an old cathedral. You've got these vaulted ceilings, and then the
Right.
roof is actually wood. Generally speaking, like the ceiling is a thin, vault or something, and then the roof is typically some kind of wood. And Oh my goodness, where was I going with that? Oh yeah, yeah. I mean, you've got basically a kind of a freestanding arch where you just have the voussoirs of the arch and nothing else, and then you could get a point load. And what you're saying there about the forces flowing within the center third of that arch makes sense to me. But when you put the arch within a wall, well, like it's within a brick wall, and there's masonry above it and all
Oh,
around it,
sure. Yeah.
then that doesn't like then it really doesn't matter in my mind, the way I actually think about it in terms of how it works in real life. That arch is not going to fail. You can do a really shallow segmental arch. You can do a pointed arch. You can do a half round arch.
Yeah, I see what you're
Um,
saying. It's interesting if you just took a solid brick wall and you just punch a hole in it, forget about the arch,
it'll
right?
stand up.
Just hit, yeah, put a hole through it. But eventually that little bit of brick above the hole will start to
Right.
arch around it. And that is the flow of forces that I'm talking about, right? Because
Right.
below that, you're getting tension in the brick or the masonry, and that's what's causing it to fall out of the arch.
Yep.
So that's that flow of forces.
Okay. And this validates kind of what I was thinking. Well, also some nuances that I learned in Spain. And by the way, when I was there with Spain, I mean these are guys they're in their 60s and stuff that have been basically studying old masonry buildings their whole lives, and they get called in to the old cathedral because there's a crack. And hey, is it going to stand up? Do we need to do anything? Do we need to put tension ties? Do we leave it? Do we need to tear it
Right.
down? So they've been studying these things for their lives. But I had always in my head before this trip referred to certain arches as stronger than other arches. And let's see, what did I say? Because you can say certain arches have less thrust. A Roman arch, which is a half round arch, is going to have less thrust than a shallow segmental arch.
Yeah, right.
And then that kind of makes sense intuitively. You look at it and you're like, okay, I can kind of like just understand, even if you don't fully understand the why. Like it kind of makes sense. But what they were talking, and I knew about catenary arches before I went, but if you hang a chain upside down, that's going to be, and you can actually move it in and out, if you imagine moving your hands in and out, that the shape of
Hmm.
the arch changes. Well, that's a catenary. You flip that upside down, and it's perfectly in tension because you're hanging
Yeah,
it as a chain.
it goes
You
in
flips upside
perfect
down,
compression.
perfectly in
That's right.
compression, and you can also thin that out and have different shapes. And this was what was fascinating to me is because I'd always thought about half round arches being quote unquote stronger than segmental. Something about it makes sense when you look at it a little bit, where you can kind of make that argument because it's like a half round arch or something. Something about it you could see the way I used to understand masonry, that it's quote unquote stronger. But the way I've learned to say it now is it's actually not stronger. Well, actually, a half round arch is less efficient than a segmental arch because the further you depart from a true catenary, the more meat you have to have within the arch to keep the flow of forces within the center
Yeah, I
third. So
think
a
that's a
half round
correct
arch is
way to think
very
about it.
unlike a chain versus well, not unlike, but you'll actually have the chain kind of fall out very easily. It's hard to keep it in the center third versus a segmental arch. There's actually more ways you can hang that chain within the segmental, or a Gothic arch, which is actually the closest to a catenary. Is actually the most efficient arch, meaning you can make it the thinnest arch, which doesn't really matter in a wall system, right? If you're in an entire brick wall, whether it's 2 rowlocks or voussoirs or 10, it really doesn't matter. But if you were doing it freestanding, with point loads and things like that, and you want the flow of forces to stay within the arch, that's where, I don't know, it's just interesting to think about, there's more about the flow of forces and efficiencies. It's not that one arch is so really stronger than the other. And ultimately, if you can keep the masonry from moving, one, you've got enough buttressing, all that, and you can keep the masonry from moving, any arch can stand there, because you actually have to have movement in a building for an arch to crack or for something to happen. Or at least that's how I'm thinking about it now.
Sure, I think you're on the right track. Absolutely.
Okay.
When I was talking about form finding and the arch shapes, and um, often what we're looking at is, how can we adjust the shape of the structure and keep everything in compression, right? And so if you think about like a Gothic arch, right, it's not a circle or a parabola or a catenary curve. It's got like a little point at the top.
Right.
So that's an example of an arch that actually has some different curvature along the
Right.
arch. You can imagine an arch where maybe you want it to kind of dip down and then go horizontal, right?
Yeah.
You don't see arches like that very often. I can't think of anything like, but if you were, you would find that flow of forces gets out of the center third if that
Right.
if that dip in the arch is too great,
Right.
and that would create an arch that would go into tension and would have some issues with it.
Yeah,
So
it's interesting. It's so
yeah,
interesting for me that starting to understand. It's so weird. Masonry is interesting because, um, if you just imagine a brick wall, you're looking at just a plain brick wall, and then you have, I don't know, just call it a 5 foot wide opening in it and an arch over it. Call it a segmental arch. And then there's 20 feet of masonry above it. You like, in your head, you kind of imagine all that weight and forces coming down. It hits the arch and then it diverts sideways. But
it's
it's not like
spreading before that. Yeah,
yeah, exactly.
yeah,
Yeah. So
yeah,
actually, you
yeah.
kind of explain that, because I'm curious if I'm, yeah. Go ahead with that. What you mean by
Well,
that?
no, yeah, it's a common kind of misunderstand. I mean, I understand where it comes from. Even a lot of structural engineers think about it that way. In our minds, we kind of chase the forces down and we follow the forces through the building. Um, but as like an aside example, I often work with concrete walls, right? And they're supported often by footings, but sometimes there's no footing at all underneath the concrete wall. Sometimes we'll span a wall from a deep foundation, a pier to a pier. And in that case, it's very clear the forces aren't coming straight down the wall and directly into the dirt. The wall is acting like a beam, right?
Hmm.
And it's distributing that load out to the piers. Similarly, in a masonry wall, well before that load hits the arch in a big solid wall, it's spread out.
Yep.
Um, and that interlocking of all the brick and just the stiffness of the wall causes that load to spread. So
Yeah.
you're
What's
right. I
interesting
mean,
about
yeah.
that is what that means is your arch isn't really carrying nearly as much weight. Say you've got 100 feet, you've got a 10 foot wide arch and 100 feet of masonry above. That arch is not carrying 100 feet of weight above it. Like you're saying, kind of is that triangle, or at least my understanding is, if it's
Yep.
a 10 foot wide arch, you make what do you call it, an equilateral triangle, and that's really ultimately about the weight that arch is carrying, because the other weight is already starting to move to the sides of it before it ever gets there in catenary fashion.
Yeah, that's exactly right. If you're going to design a steel lintel, which is, we could talk about that, but if you're going to design a steel lintel above a window, we really only have to look at that triangle of brick that's above it, that
Yeah.
equilateral, 45-degree from the ends of the angle. And that weight of that is all that hits that lintel.
Yeah.
So lintels are often very over designed for
Right,
what they
I
actually see.
believe that. I did it
Yeah.
once myself, just I was so nervous about, and of course engineers, but I mean, like, I didn't know, I didn't fully understand, and so I even did a relief arch above it, because I was like so
Yeah.
scared about using metal, and just it's kind of funny, but the
Well, I might maybe we could talk about brick veneer for a minute, but like brick veneer throws a wrench in kind of all this because with brick veneer you've got to have control joints, and often the control joints are at the windows, and
yeah,
so now it's like, well, you don't have any way to resist the thrust. So
right,
is it going to arch over the lintel? Probably not. And so now you've
right.
got to over design all your lintels for this wall of
Oh, see,
brick
that's really
that has nowhere
interesting.
else to go. Right.
Yeah, that's another kind of nuance there about not per se veneer, but something I learned or realized is, say you do put in a solid stone, and I think most engineers would, want to throw up if I told them this, but like putting in a solid unreinforced lintel, stone lintel above a window,
Sure.
terrifying, right? I'm just kidding. But it actually, I mean, I think, that functions as a beam when you put it in, is then weight comes in, there's no thrust off that because the weight's coming, straight down because you've got a beam, just
Yeah,
like you would
right.
with metal coming straight down, like you're saying. But this was interesting, and this was what I was talking to some of these experts about is, yeah, but what happens if that lintel cracks just a little bit? Well, the building's not going to fall down unless like there's substantial movement and the walls falling away. There's really no way for masonry to fail if you can keep the walls from moving in some ways. Well, structurally, water and stuff can damage
Yeah,
something, but
right.
the moment the lintel cracks, it's no longer acting as a beam, it's actually acting as an arch. Like it's arching within that stone that might be two pieces together, and there's one side kind of slipped down and a little crack in between it. It's no longer acting as a beam, it's actually acting as an arch. And then it's just, you can't have any, it's not going to slide, so it actually holds itself up. But
Yeah, I
what's
think what's
interesting about that
happening.
is I used to think, oh, I can put a lintel closer to a wall and need less buttressing
Oh,
than
I
a
see.
segmental arch or something, which is true. But if that stone were to crack and suddenly that thing starts arching and you can't control that, it was just a kind of like oh, that's interesting. Like I hadn't thought about that.
Yeah, gotcha. Yeah, I think you're right. I mean, when the lintel cracks, right, the brick above it tries to move down with it, and as soon as that happens, it starts to arch again.
Yeah,
Now, if the question is like the lintel itself, if it has no steel inside of it and it cracks, there's nothing resisting the tension on the bottom side of that lintel. So it would fail, but for the masonry above not coming down with it.
exactly, because that's what I mean. If you keep your walls from moving, that lintel, even if it cracks and starts to fall, it can't actually fall because the masonry over here is holding it in place, and then it
Oh,
can't
right.
slide past each other. It can't move out. The outside can't move up. And so that's what I see cracked lintels all the time. It's funny because we misunderstand masonry so much in the United States. We look at cracks and it's like, oh my gosh, the masonry's failing. We actually put this in our contracts, but it's like masonry cracks. All masonry cracks over time
Right.
because
That's awesome.
any tension introduced into it, the only way for masonry to relieve tension is to crack. And then it goes back into equilibrium. Well, hopefully. So I say 99.9% of cracks are non structural. Would you agree with that or disagree? I mean, I'm saying arbitrarily saying 99%, like maybe of well
Yeah,
built buildings.
yeah, there's a lot of masonry is kind of like concrete in this respect. Concrete always cracks. And yeah, masonry will crack. If you're using the right mortars and things, sometimes those cracks can kind of heal themselves a bit. But
Right.
when there's building movement, we'll see diagonal cracks, and that's a
Mm-hmm.
structural concern. That's usually a sign of settlement,
Right.
big diagonal cracks. But often, like a vertical crack is usually just a sign of shrinkage,
Yeah.
typically.
Yeah. I actually had one of my first big arches crack, and it scared the crap out of me. Um, and I had uh, Wallace Engineering. Do you know
Oh,
Wallace
sure.
Engineering?
Yeah, they
And
they
this,
have a Kansas City office. Yeah.
yeah, okay. So and at the time, I mean, this is a while ago. Tom Wallace, like the guy that started it, like he was just curious because I was like, oh, that's pretty cool, and I had him come assess it, and he was like, oh, you're totally fine. Don't do anything.
Great.
I was like, oh, awesome. And then, but it was funny because that's where I started really understanding masonry better because I just lay at bed at night, like, why did it crack? Like you're just sitting there thinking about this wall and how it works and things. And all it was is just like one side of the arch settled a little bit. And this is interesting because it's allowed by engineering. But what we did is imagine a rectangle of a house. So just a simple rectangle of a house
Okay.
and then cut that rectangle in half with what I would call kind of like you see it in a lot of our houses if you're on Instagram or something, just like we call it a buttressing wall on the inside where it's just a big arch on the inside.
Yeah.
Basically just cuts the rectangle in half and then also cuts the floor plane in half a little bit and you get this big brick arch inside, very pretty. And a lot of these arches, we do this in a lot of our houses, they're 10 to 12 feet wide. Well, even engineered, right? Like the foundation, well, we didn't carry the footing underneath that 12 foot of arch because why are you going to waste all that concrete? So it's just like we did footing for where the spring, where the arch started, where it went
Right.
to. And then there was nothing in between. Well, then what happens is one side can differentially settle compared to the other side. And so now we never do that. We always, and like this is funny because once again, you can have it engineered and they might not do that. But now we just carry that, even if it's a 20-foot wide arch, we'll carry that footing all the way across and connect it with rebar to make sure. And granted, you could still get differential settling, but it makes it way, 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 way harder. And we have not had
Yeah.
any cracks since.
Yeah, the way I think about that as a structural engineer, I try to size my footings for equal stress, right? So I try to chase all the loads down the building, and then when those loads hit the ground, I adjust the size of the footing so that I'm applying the same amount of stress to the
Ah,
subsoil everywhere I go. So in your case, like the arch, right? One way to deal with that is exactly like you said. You could just run the footing all the way through, reinforce it, and that distributes that load over that larger area. The other way to do it would be like at the ends of the arch, you could have spread footings that are wider, larger, and then sized so that the soil stress is the same as the rest of the wall.
got
So
it.
in
Okay.
plan, you would see maybe your typical footing is, I don't know, 2.5 foot wide, but then at the arch, maybe you have like a 5 by 5 foot footing, something like that.
Got it. Okay. That's
Yeah.
very interesting. Well, I
Yeah.
wanted to say one more thing on the, because it helped me understand it for anyone that might be listening. You know, once again, kind of going back to that arch, this idea of the arch carrying all the weight or not carrying all the weight, and you might be thinking like, how is it not carrying all the weight? Well, or this idea of like, yeah, the weight comes down, hits the arch, and then it goes sideways around to the sides. But if you just imagine I don't know, call it a 10-foot high garden wall, just to call it a double wide brick wall, 2 brick thick wall, 10 feet
Right.
tall, and you've just got all the brick laid just normally how you would see on a building. Okay, yeah, you can make this sense. All that force is going straight to the ground. Just everything's going vertically, right down to the ground. And then now change the brick and turn it, up on end, and what we would call a soldier course. Do the same thing. The forces flow through it the exact same way. Turn them on a diagonal. The forces flow through it exactly the same way. Build a bunch of arches into the brick wall, but it's all a solid brick wall. There's no actual openings. Those forces still just flow straight down because it's not like going, oh, I hit this brick that's turned a different direction. Now I'm going to go sideways, right? Like it's still, in that sense, it's a monolithic wall to the forces. Or at least, once again, I'm kind of saying this because this is how I'm understanding it now, and curious if you would agree with that.
Yeah, so well, often with masonry, right, we're trying to have a mortar and a masonry unit that is, similar strength. The mortar usually a little less than the masonry unit. And when they bond together, um, those two elements now have similar strength and similar stiffness. So the thing with structural engineering and with load path is that the load will always follow the path of highest stiffness. So if you put something very stiff in
Mm,
in a wall, it attracts load, right? Um, and so you know, a clay masonry unit has the same stiffness no matter which way you push and pull on it. So it doesn't really matter in a wall application how you orient that brick, as far as how the forces flow through the wall. You're right about that. Kind of what does end up mattering is, when you have, uh, the bricks will tie into each other, and so like if when you punch a hole in a wall, they'll interlock, and that interlocking of
right.
the bricks can create, it's a kind of an arching action. And so that's a little different. That's a little different than what you're getting at anyway.
Yeah.
But I agree with your fundamental insight there
Okay.
that, yeah, forces
That was
flow
mind. That was,
regardless.
because I already, when I figured that out, like I already, just because I've been doing this a while, like I understand masonry differently than most people. I have a very hands on, understanding.
Yeah.
But that one was still like oh my gosh, like it was a complete, it kind of blew my mind in the moment of how I was missing something so big, but really kind of exciting too to start understanding masonry differently. Um, well, because when you actually really understand something, you can start manipulating and playing and inventing and things more. So,
Right.
um, would most engineers understand? I mean, I'm sure if you told them, but like, would they know that if you just what we just talked about?
Hmm. Um, I think they might. I mean, we often think of masonry pretty monolithically as far as the stress when we're analyzing the stresses in a masonry wall. So that's not that uncommon. We have these things we call, allowable stresses, right? So we'll calculate for a given masonry unit and a given mortar what the allowable stress is in that wall. And it doesn't really matter the orientation of the masonry units. We're always checking the same stress everywhere in that wall.
Got it. Are you familiar with Hyman? Um, Hyman, he's what is it? Jack Weiss Hyman. He's
Is
still
he a
alive today. He's
engineer
very old.
or what does he do?
Yes, engineer and graphic statics, and he's written like the stone skeleton. He's kind of like the structural masonry master, but he's very technical. So like it's really hard to understand just as a layperson. Like I have trouble understanding.
How do
But
you
he
spell his name? I'm gonna do a quick Google.
Heyman. I've got a couple of his books. Yeah, because he actually, this is really interesting. This was what was repeated in Spain over and over again. Is Hyman, Hyman, Hyman. Like you've got
Hmm.
to understand him if you want to understand masonry. And he has three rules about masonry when you're designing. He says one, assume that it has infinite compression. Obviously, it doesn't. Like it can technically fail, but just in terms of practicality, you're never going to fail in compression with masonry because you can build it so high, you know, without
Right.
failing. And if you're talking about skyscrapers, fine. You know, maybe at some point you have to worry about it, but for the most part, infinite compression. Two, no tension. So he just, even though technically masonry has the ability to have some tension, he just says like assume there's zero tension. And then three, assume no sliding when you're designing, you know, sliding
Yep.
between things. And obviously that can happen. And by the way, sliding could be hugely detrimental. But when you're trying to figure out if a building, like how to design a building, those are his kind of like three tenets of structural masonry. Um, and he's someone I still want to learn more and read more. But he talks about all this kind of stuff that we're talking about too, and
I love
flying
that you
buttresses
brought
and
it up.
things.
Yeah, I've seen this book before and I don't own it and I'm not familiar with his work, so I'm gonna check it out.
Cool.
That's really cool.
Yeah, I'll be curious if you ever do get into that. I would love to talk to you about it because that's one where I think you would understand so much more than me reading it. uh, you know, we've mentioned a couple times, and I think this is a pretty practical one. I'm curious your take on mortar. I'm guessing we're fairly come from a similar place on it, just from what I heard you say.
Sure.
But what is your kind of take on mortars, and in your opinion, what are the best mortars?
Yeah, I mean, there's a lot of confusion on this topic, and it's probably good to try to bring some clarity to the issue. So, in the United States, we have yeah, how most engineers think about it is, the word mason, right? So Mason, the different types of mortars, and um, M is like the strongest of the strong mortars. It's high cement content. Um, and then, as you go, S is structural. It's also high strength. N is lower strength. O is even lower. There's also
Right.
a K, which is very low, very low. I think
Oh,
it's
I hadn't even heard of a
masonry
K. That's
work.
interesting. I thought O was
Yeah.
the softest.
Yeah. Let's see. Mason
Or I guess every other letter.
Work. Yeah.
I
Right.
always forget too.
Yeah.
I just
So
remember
K.
MSNO.
Yeah, K is on the lowest end. But every one of those is cement-based mortar. I mean, that's just what we do in America. That's
Right. Cement
it's
being Portland.
Portland cement, right? So they have different amounts, right? So type N is 1 part cement, 1 part lime. Type S lime, hydrated lime, which I'm going to talk about in a second, and then sand. And type S or type that's type N. Type S has half as much lime, and type O um, has that much less again
Yeah, we
of
actually
lime per
make that. I'm
quarter.
curious because we make that. It's kind of like our best of not the best, like the best cost effective thing to do
Yeah.
for anyone out there too. Like rather than buying a type S or a type N that's pre-mixed from the store, we'll mix a type O on site that is
Oh,
one
great.
one part Portland, 2 parts type S lime. And technically they say it's 9 parts sand in the book, but I'm
Yeah,
skeptical of that and think
H9.
it's more
Yeah.
like 8. But
Yeah, technically, I think you can adjust that and still
right.
be type O. Yeah.
And that's
Um,
something like 350 psi, which I understand sounds really low to people because like concrete's 3,500, you know. But in the context
right.
of the building and the way it's distributed, when you're building a few story buildings, you're not worried about 350 psi actually pencils out,
Yeah.
from my understanding.
Yeah. I like to just, if I know the masonry unit that I'm working with, I want to make sure that whatever mortar I use is less than that masonry unit. You don't want to have a higher strength mortar than masonry unit.
Right.
Um, it can lead to a lot of different issues. But that's just okay. That's just cement-based mortars. In historic preservation, we have lime-based mortars that are in all these old buildings, and you don't want to be mixing cement-based mortars and lime-based mortars unless if you're super careful about having a mortar that is very similar stiffness to the other
Right.
mortar in there. Otherwise, the load that's coming down the wall, I already said load will chase the path of highest stiffness, right? So now it's if you mix a high strength, high stiff mortar in with an existing old lime mortar, that load is going to shift over and try to force its way through that little bit of tuck pointing that you did.
Fascinating. That's new for me. Okay.
Yeah. So we want those to match. The other thing that happens is a high cement mortar, like a Type S mortar, will hold water behind it,
Right.
and so we can actually trap water, and then you can get freeze thaw damage in that masonry, right, from water. It's also the more Portland cement you use, the more likely that mortar is to crack, and the less able it is to heal itself too. The lime in that mortar will help kind of fuse back together the micro cracks that happen in that. Um, and so that cracking also allows a path for water into the joint, right, which can
Right.
then saturate and leach out the lime mortar that's behind it. So there's a lot of things to think about when you're using different mortars. But um, in Europe, they're still using lime-based mortars without any cement, and those are different.
Yeah.
When you go to Home Depot and you buy lime, Type S lime, that is a hydrated lime. If you mix that lime with sand, it's never going to set up, right? It looks like mortar, it never sets up. That's very different than hydraulic lime. Um, or natural, there's non-hydraulic, there's natural hydraulic lime, lime putty, it's also called. All these have a natural pozzolan or like fly ash, slag, brick dust in them that will allow them to set up and act as a mortar. So those kind of mortars are great for soft masonry and they're very common in Europe. But they're pretty hard to attain here. I don't know if you've had luck trying to
It's
source
about
them.
50 bucks a bag. You can get it pretty easily, but it's $50 a bag. And just to compare that, you can go to the store and buy a Type N for 12 bucks a bag. So it's,
Yeah, exactly,
boy,
right. So I often recommend that people use Type N or Type O, and let's take a look at the masonry units that you're using and
okay.
try to think through that. But the one issue with lime mortars from Europe or even a Type O mortar is really just kind of freeze thaw and durability over time in an exterior environment. The mortar fails, which is exactly what you want, but it's just going to fail a little sooner
Right.
than maybe a Type N might in an
Right.
exterior wall application. So
That's what's
Type N
interesting.
can still be good from a longer term durability of the wall, or I should say, not really durability, but you're going to have to repoint the wall more often if you're using a
Right.
softer mortar.
But yeah, it's hard, but it's like you got to repoint it more often. But it might, if it is maintained, may actually last longer in the
Yeah,
long
that's right.
run, which is
Yeah,
interesting. But I mean, I totally like the Type S or Type N, on repointing on an old historic building. My gosh, I mean, I see that all over Oklahoma City. You'll walk by and you see this brick spalling. I mean, it happens
yeah,
very quickly.
especially yeah.
I didn't know about the following the path of the stiffness, which is really fascinating. I hadn't realized that. That makes sense to me. But yeah, the water one and the freeze thaw, boy. But on that note, it's interesting because old brick, these brick that are
Mhm.
100 years old or more, those are a lot of those are 2,000 psi, maybe 3,000 psi versus modern brick. I mean, the brick we're using are over 6,000 psi. So even just straight
Oh,
up
yeah.
Portland concrete that you'd be pouring a driveway with, that's 3,500 psi. The brick is still way harder than the Portland. So what's your opinion of that? And this is where I really don't know, and I'm not sure anyone really knows. Everyone's got opinions, but like because we haven't really tested it. But some people will say, well, it's stronger, so it's better, more durable. Well, because it's modern brick, it doesn't matter as much. And now the Portland is actually better because we've got harder brick, and that way, yeah, you don't have to tuck point as much, like with the lime mortar, et cetera, et cetera. What do you think about? Yeah, what's kind of your take on that harder brick? Does that make Portland okay, better? Is lime still preferable?
Sure. Yeah. I think the harder brick, I think they're on the market more now because in a cavity wall situation, those bricks are exposed to much higher degrees of freeze thaw. And a porous brick in that application, imagine a brick full of water and then freezes, right? It's gonna bust apart more easily. Um, and a highly porous brick is going to allow more water into it. So the higher strength bricks also tend to be less porous, and also then less susceptible to freeze thaw damage.
Right.
So I think that's why in the market you're seeing higher strength bricks are more common. It does mean also that they're more agreeable to cement mortars as a result, right? Because they have a higher strength. So I think that's okay. I think you can use type N and type S in a cavity wall and be fine. And in a mass wall like what you're doing, um, you want to have that vapor, the water to be able to come in and come out of that wall.
Yeah.
You want it to be able to dry in both ways. And so more porous bricks and more porous mortars work well in a big mass wall as a result. So I think
Yeah.
that seems more appropriate there. But yeah, I think a lot of the higher strength brick, like I said, and mortars are really a function of how we're using them today, which is cavity wall construction
Right.
primarily.
And it seems like it would still be good in structural masonry, just that once again, the more water you keep out without sealing something also that when water gets in, it
Yeah,
doesn't, it keeps liquid water out, but it allows water vapor, water gas in and out.
yeah,
It
that's
seems
right.
like harder brick, even for structural masonry, would be a very good idea. And that's where I kind of go, I just wonder, like, okay, if you've got a harder brick that lets in less water, might it be better to have a harder mortar that lets in less water too? But I don't know, and I'll tell you kind of
Right.
like just how we think about it and what we do. It's if we do use a pre-blended mortar, and budget's kind of the main thing here, is we'll use a type N, from the store, type N. So it's the softest you can buy from the
Yep.
store because you can't even find type O. So that's kind of our, that's our lowest tier, but we feel good about it still with modern brick. We would not do that with a reclaimed brick, to be clear. The second version we'll do that's a little bit more expensive but still doable is we'll buy type 1-2 Portland, type S lime, and the sand. So it's the type O mortar where it's 1 part Portland, 2 parts type S lime, then 8 or 9 parts sand. And I
Yeah.
think that's pretty solid because at least it's got twice as much lime as Portland. And then the third kind, which is a more recent discovery in the past 2 years, because these NHLs, the natural hydraulic limes out of Europe, are
Right.
50, $60 a bag. And heck, I don't even know those bags are as big. So, I mean, it's just outrageously expensive unless you're going to be just tuck pointing a few things, right, on a historic building, and it's worth it. But Graymont, out of their plant in, I think, Ohio, has a PHL, a pozzolanic hydraulic lime. They've got a 3.5 and a 5.0, and they're using metakaolin for their pozzolan. So it's no Portland, no cement, and it's just
Right.
real lime and metakaolin, which is supposed to be a very good pozzolan. It gives the hydraulic set. And so that's what we've used on a couple of our buildings. And when we're using reclaimed brick, we'll either do that or the type O blend if we're using a reclaimed brick. But that PHL is really interesting. Do you have an experience with because the problem is I like it. I like the idea of it. I've talked to a few people that really think it's awesome, but like so few people know about masonry in this country that it's
Hmm.
you know
Right. Yeah, I get it. So the question is about pozzolan-based lime mortars.
yeah.
I don't know much about them. I
Okay.
know, we've been doing this in concrete for a long time where we've been trading off cement for fly ash, slag, metakaolin, um, silica fumes, another one. Um,
Oh, so y'all
and
use metakaolin in concrete
yeah, it's
stuff.
in concrete. Yeah,
Got it.
it's
Okay.
not it's not common. I think
It's a clay product, right, or some kind,
yeah, it's
metakaolin?
yeah, it's similar to like like brick dust
Okay.
is also a pozzolan, right?
Right. I remember the
Um,
Romans, I think, did that for their
yeah, and
lime.
it's a clay-based product. It's complicated. I don't know a lot of the nuances of it, but I kind of think about it as similar to like what a brick dust pozzolan is.
Okay, got it.
Yeah.
And I don't know, you might not know if this is true or not, but my current understanding is what gives lime a hydraulic set is the amount of impurities in it, and I'm going to miss the whatever the molecules like because whatever it is,
You
calcium
probably know more about that
whatever
than
I
I do.
forget.
Yeah.
Do what is
I don't
that
I don't know about
okay?
yeah. Yeah.
Yeah, and what I've
I know that it's a
heard,
thing, but I'm
okay,
not
yeah,
familiar with it.
I don't know if this is true. So if you ever hear anything, keep an ear out. But like what I've heard is that in Europe they have, well, their lime is less pure. So like they have a bunch of NHL. In the
Gotcha.
US,
Yeah.
our lime is actually a lot more pure, or at least what we're mining. So we actually have to add pozzolans to it to give it a hydraulic set, which is
Oh,
just
gotcha.
interesting.
It
And
is
that's
curious to
kind of
me
anecdotal.
why.
I heard that from like one or two people years ago, but it
Okay,
made sense to
gotcha.
me.
Yeah, I'm not familiar with that, but it has been curious to me why it's so hard for us to get the same lime mortar that they're using in Europe. Like,
Yeah.
what's the deal? What's the
Well,
deal,
and so
US?
this
Yeah,
is actually one other interesting thing, and I mean we're at an hour, so I'll kind of want to wrap in the next 10 minutes, and we're just gonna have to do another one
sure.
because I've gotten through like a quarter of my stuff. But um, oh shoot, where was I going? Where was I going?
Uh,
You were asking about so why don't we have lime? And this is I've talked to old masons in the U.S. They'll come on one of our job sites, and maybe they're 50s or 60, 60s probably, and they'll be kind of blown away what we're doing, and they'll say, "Man, I remember," and maybe they're a little older, 60s, 70s or something, and they'll say, "Man, I remember we used to do this. We'd show up on a job site. There's a foundation there and a footing, and we'd start laying brick." And I always ask people, what happened? What changed? And a lot of people, like more than just a few, have indicated they think steel lobbying and concrete lobbying played a huge role, if not the main role. And I've actually heard from other people, and these are trustworthy people, but I'm kind of being cautious because I don't know these as facts, but that even the Portland industry bought up most of our lime and stuff like that, and they're just not mining it. And so there's all sorts of little conspiracy things around steel in Portland, which is kind of funny. But I'm also open to it because so much of it is weird. Like you're just going, what happened? Like one day we're doing all these things, and then the next day, boom, done. Like Guastavino did over 1,000 buildings across 32 states in the United States 100 years ago. Most of those are still standing today that aren't torn down. They're shockingly amazing. The St. John's dome that he did 100 years ago in New York, it's 130-foot diameter. He's using 5 inches of thin clay tile and zero steel or reinforcing. The Duomo in Florence is
yeah, it's
146
incredible.
foot diameter. It took him 15 years to build. He did this in 15 weeks without centering or formwork, and it's still standing. And they chose him to do that because it was the cheapest option to do it. And now, like, you would be looked at like you're an insane person if you were to even just ask to do something like that. Sorry, that was kind of
I'm
a
not sure. No, I love it. I'm not sure what to say. I'll say this for a very, very long time. Concrete in America was incredibly cheap, right? It's incredibly cheap. It's still fairly cheap. But when with that building material that is so powerful in so many ways for construction, I mean, it's pretty honestly concrete and steel together. It's crazy what we've done with that material,
yeah.
and it's been so cheap for so long that I think economics was a big part of it. Maybe there was a conspiracy too. I will say, I also do a lot of work with mass timber. We should talk about timber sometime. I think
Oh
that would be
yeah.
cool. But the cement industry, the concrete industry, um, they put all kinds of marketing about how mass timber buildings were unsafe, and they were incredibly scared about it, and did
Right.
everything in their power to try to limit designers from designing around it.
Right. And see, that's what I wonder about steel too, because it's like steel is an absolutely incredible material. We have done
Yeah.
the modern world is, I mean, just mind-boggling, just amazing, right? We can launch rockets into space. I look at skyscrapers and I'm just like, how are we able to do stuff like this? And then I pass a 12-foot garden wall in Oklahoma City that's built by the government and fairly new, and it's falling apart because they put a bunch of steel in it. And it's
Oh,
like a
yeah.
freaking garden wall. And then I'll
It's
post about it and
right.
say, guys, I'm not an engineer. I don't put steel in the buildings because, by the way, when steel rusts, it expands 4 times its original size. It blows out the masonry. Failing infrastructure in America is not failing concrete, it's failing rebar. And then I'll
100%.
literally have
Yeah.
engineers message back angrily, arguing with me about how it was the right thing to put that steel in that wall. I'm going, I don't even know how to, it just doesn't make sense to me.
Yeah, you're right about that, and they're all wrong. So as
That
soon as you
actually really
put,
helps me to hear because I'm
yeah,
always worried I'm wrong.
man, okay, as soon as you put steel in concrete or masonry, you're limiting the life of that structure if it's exposed to moisture. Now, like in an interior environment, you got a concrete building, concrete columns inside a roof, under a roof, and behind walls. Yeah, that's gonna last forever, as long as it's, stays dry. But yeah, in an exterior application, eventually over time, that cement, that concrete is going to carbonate. The pH level in that concrete is going to change, it's going to drop, and then that steel will start to rust and
Yeah.
expand. I think it's more than 4 times. Maybe it's 4 times, but yeah,
I've heard 7 too, but I've heard
yeah,
4 to 7.
yeah. And so you'll see rust jacking, and yeah, it'll blow apart your concrete and your masonry. And so yeah, I think as structural engineers, especially, we should be really careful when we specify steel, any steel in an exposed environment like that. We're limiting the life of that structure by doing that for sure.
Got it. And I have a question there because this is what I wonder because I definitely know about it in exterior walls, right? Like, although I found this out recently, I don't know if it's well. They were saying that. Hold on, these were engineers. These were actually when it was in Spain, but it was they were saying that steel, like if you actually just leave it in water, it will last a lot longer than if you're like putting it in water, drying it out, putting it in water, drying it out. So that's true. Okay.
Yeah, the chemical reaction requires water and air, oxygen.
Okay.
And so take one of those away, and you're not going to get the rust.
What is the technical term for like some steel resting? It's carbonizing. What is it doing? What's the
I just call it resting. I forget the
Okay.
technical term.
Good. We'll just leave it at
Yeah,
that.
yeah, great.
But here's my other question because you mentioned and this was actually something I really wanted to ask you is yeah, when you do use steel correctly, right, in the right
Right.
application, it is an amazing material. And say you've got concrete columns in a building or something. I always kind of was thinking like besides humidity and stuff like that, like man, it seems like those could last a pretty dang long time. But these people I met recently said yes, it will last a lot longer than an exterior wall. But ultimately, they said the exact same thing you just said about the concrete, its pH level
Carbonates.
changing.
Yeah.
And what is it, carbonizing? Because it's
Yeah,
absorbing carbon.
right. Carbonizes.
Oh,
Yeah.
so it's carbonizing, and then that steel is still going to rest because of that carbonization around it. Is that
Yeah.
true?
Yeah, that's true. So
It's
there's
just
it slowly over time there's a I forget what chemical you put, but you can cut a piece of concrete open, and you can apply this chemical to it, and it'll turn the concrete pink, and over time the pink represents the the depth of the carbonation of that concrete. And
mm,
so that goes deeper and deeper and deeper over time. So part of what we do in concrete design is we set the rebar back from the face of concrete by a dimension, right? In exterior concrete, it's 1.5 inches, 2 inches, even 3 inches. And we do that because of that carbonation, and also because of cracks and water infiltration that can bring water in touch with that rebar. So yeah, so inside of a building, we're stepped back 1.5 inches, 2 inches on our columns. And it's going to take an incredibly long time for that carbonation layer to reach that steel because it's harder for it to go deeper and deeper, right? It happens kind
got
of
it.
quicker at the surface, and then it slows down
Because it
as it
actually
goes
has to
deeper and deeper.
absorb the carb. Right, right. Which
Right.
is why a
Yeah.
hydraulic set and mortar is so important. So you can keep building your wall quickly. Because if it's carbonation, it
Right.
can't cure in the middle of the wall. Because if it's a
Yeah.
thick
Right.
wall, okay,
Yeah.
that's kind of the same. Am I comparing that
Yeah, that's right.
correctly? Okay,
Hydraulic is water set. With mortars, there's also like non-hydraulic mortars that set through exposure to the air, which
right.
is interesting, I think.
Carbonation.
Yeah, through
Yeah,
carbonation.
right.
But
Like
yeah,
the Type S line.
yeah, yeah. Well, right. Type S lime mixed with the Type S lime, like from Home Depot, mixed with the pozzolan. Yeah, that'll
Oh,
set.
you still have to mix it with puzzle. Like even I thought lime with sand was actually you can cure it. It'll just be it would be through carbonation because we've just kind of like painted it on stuff before and it does dry out and harden up, but it's not like
Mhm.
hard.
Yeah, the Type S is that you buy from Home Depot is special. It's
Right,
a
special.
hydrated lime. It goes through this process where it won't ever set up by itself with water. It'll dry out and it might crust, but it won't
Oh,
actually
I
set up
see.
in any sort of structural way.
Okay, I'm glad
Yeah,
that helps. It's been a while since I was thinking about that. Okay.
yeah,
I'm gonna ask you a couple more things because we're talking about
sure.
steel. Well, three more things.
Sure.
So a skyscraper, for example, that's steel structure, all that.
Steel and concrete. Yeah.
Can those last like, I mean, 500, 1,000 years?
I mean, there's a lot in that question because any structure has to be maintained,
Right.
and some structures can last longer with less maintenance than others. We've already talked about that. A big steel structure, like I've also already said that it needs to be a building that's loved, right? Or else it's not
Right.
going to be maintained. I think that's
Yeah.
important. Um, but it's going to be the facade, right? So it's going to be the glass, you got sealant joints, all of that has to be replaced over time. It's going to be the detailing of the roof at the parapet to the walls. It's going to be all, that whole envelope has to be cared for over the life of that structure if it's going to have any chance of lasting 1,000 years. But there's nothing about the structure itself that I think would prohibit it from lasting
Got it.
an incredibly long time. Yeah,
Right.
1,000 years, maybe.
Right. That's a hard timeline.
Yeah, it's
I mean,
it's
you have
real
no idea what's, yeah. Yeah.
right.
Cool. Um, just out of we'll pick it up on the next time we talk, but excuse me, are you familiar with GFRP rebar at all? Glass
Yeah,
fiber
glass
reinforced
fiber
polymer.
reinforced.
Yeah.
Yeah, yeah.
Have you all used that?
We actually talked about it in our office here recently. It's an interesting material. You can't field bend it. So if you need hooks and things, it may not be the best choice. But for flat work, it could make a lot of sense. It doesn't have good fire resistance, I believe. I think it softens under a fire event. So in a
Mm-hmm.
building where you might need your concrete to have a 1 hour or 2 hour rating, I think there might be some issues with it there. Um, but yeah, like imagine like for a slab on grade or a grade beam or I can imagine an exterior environment where it might be exposed to the elements. It could make a lot of sense. Yeah.
Cool. And we'll talk about it more next time, but that's what we've been using for, I don't know, gosh, 6 years now,
Oh,
is
you've been using
GFRP
it.
rebar in our
Oh,
buildings.
that's
And
great.
it's
Okay.
interesting because I feel like when we first started using it, it was like really under the radar. And in just 6 years now, like there's a couple local stores that are stocking it. Now it's
Oh,
not the
wow.
size we need, but it's like 7/16 or something. So, number fours, and we generally use number
Okay.
sixes, for our walls, like vertical reinforcements and bond beams. But I will say, totally right on the bending. But thankfully in our application, we like need straight ones and then we just need corners. So we just order the corners, like 30
Oh,
inch
yeah.
bent corners. And it's actually really nice because then you don't have to bend it. And working with what I love about it is it weighs 75% less. So like, you
Oh,
can take a number
sure.
six, a 3/4 inch stick that's 20 feet long, and I could carry a bundle on my shoulder versus one piece of steel. I would carry it and it would be like, oh, and then
Hey,
trying to like
yeah, that's really
maneuver it
cool.
and get it around. And, it's
So,
interesting.
are you using it in like a foundation, like a concrete foundation, or are you using it in your masonry walls?
We've done both, and what we're trying to move to is only GFRP in foundation and walls. But we've just been doing it in walls mainly, and then foundation when budget allows. Although at this point, it's about the same price as steel. So, or at least last time I checked.
Yeah, interesting. I have more questions now. I
Okay,
unfortunately have to go. I got to take kids on a soccer
cool.
carpool here momentarily, but
Okay, well, let me
maybe we'll
just
have to
show
do
you
it
this
again.
one thing because I
Sure.
want to get you nerded out so that we can get back on here and talk. Let me share my screen. I know anyone listening is not going to be able to see this, but I'll describe it. And okay, let's see how I can do this. Window. Okay, here we are. Share. What to do? Okay, well, while that is loading, Trevor, I'm showing you. There's this guy, Peter Block Research Group out of Zurich, and they're playing with graphic statics
Yeah,
along with John
I saw
Oxendorf at
this. Yeah.
MIT. And this is a floor system that they are installing in high rise. And I think it's already in there. So it's multiple stories. This is a concrete floor system that's 5 pieces. They're cast pieces, and they're just lowering them into place. And then that middle piece gets put in last. The thin parts between the ribs is an inch thick. And on top of that, they're using lightweight concrete and there's zero steel or anything in here. The only steel would be exterior tie bars around it in some applications, or if your building envelope already has that. But basically, that is entirely in compression, and it reduces the amount of steel and concrete that they need for their floor systems by something like 80% or something like that, which I had never realized that floor systems in high rises and big commercial buildings were such a huge part of the cost, materials, labor, and carbon even of a
Oh yeah, for
project.
sure,
And so it
carbon.
was
Yeah,
just these massive reductions. I just thought this was the coolest freaking thing I had seen in a long time.
I
Are
love
you
it.
familiar with this?
I'm only familiar as of this week. I saw something about this and looked into it. I mean, it is really incredible. Like you said, like thrust, like back to that early conversation, this only works because of the thrust at the perimeter. So you have to design a whole, your whole building. These all have to be very carefully laid out in a way where all that thrust can be resolved, right,
Yeah,
through
yeah,
tie rods or
right.
through other structure. But yeah, I mean, it's super cool.
Right. Like I keep going. The applications. I mean, they're doing other stuff. This is in
Yeah,
Texas, I think, and this is
I've
just
seen this.
you've
Yeah,
seen that, and it's just
yeah.
amazing because they're designing this with graphic statics. Now they're using Grasshopper and other things, and I think some of them
Mm.
do more. I don't know enough to speak to that. You would know way more, but it's really impressive. What you can do when you get the geometry and the proportions right. The efficiency and strength of a structure that you can make. Like it's shocking to me, and it's such a cool thing that I feel like is missing, completely missing in modern engineering. Like I don't know if that's true or not. Like, do you think stuff like this has a real world application today in the 21st century?
Yeah, it's it's hard, right? Because there's so much momentum, inertia going in the direction that we've been going for the past 100 years. So it's really hard to change things. But as we get an individual project, one individual project after another individual project, where these things start to make sense again, like especially this floor system that you had on the screen. Um, I could see that having pretty wide ranging use in a even a high-rise building, right? It could
Yeah,
reduce the weight and could reduce the cost and even the speed of construction because those are all prefabricated.
yeah,
Um, it's similar to kind of what I'm seeing with mass timber too. Is like as the bugs get worked out and we're figuring out how to use it better, like I think we're going to see more and more buildings
cool.
use those structures. But unfortunately, it just takes a lot of time for people to wrap their heads around it.
Right,
You got to test it, you got to prove that it's going to
right.
work. Someone's got to actually go out and build it, and everybody's watching, and
Yeah, yeah.
you
Fail,
know,
and you fail very loudly.
yeah,
Just doesn't help.
exactly. Yeah,
That's kind of
but
the exciting part of it all for us. It's like, how do being the age that I'm 35, and when you grow up in the world as it is, you kind of feel like the world's all figured out. You can
mm,
travel, go to Africa, and take a picture on your Instagram, and it's posted for the world. You can fly, go into space. Just insane. And we were on the verge of AI, right? And it just feels like there's nothing left to like truly pioneer. But like, the older I get, the more I don't believe that. The more I'm like, oh my gosh, there's so much more to do, so much more to learn, so much more to pioneer, so much more invention and innovation that needs to be had. Like we had like this skyrocketing amount, and I feel like there's almost a bit of a plateau. And it's like, what is the next kind of push going to be? But anyway, I know
no,
you
it's
got to
cool.
go get your
Yeah,
kids.
yeah,
I could do this for 4 more hours, so really appreciate it, and I look forward to hopping on here again sometime if you're up for it.
yeah. Austin, I had a blast. Happy to chat about other topics, structural engineering or otherwise. We have a lot of similar interests I see
Yeah,
here too, so I think that's a really cool thing.
cool. Well, thanks, Trevor, and yeah, we'll talk to you again soon.
Great, thanks. Talk to you
Bye.
later.